Okay, so Assalamu alaikum. Uh, today, in today's lecture, we will study about chapter 9. Chapter 9 is basically about the page diagrams. Okay, so in the previous lecture, we looked at the eutectic binary alloys and all the other phase diagrams, right? So phase diagram looked like this, that it was composed of two portions. First, we have to look at this, that it was the liquidus line and this was the mixed region and this was the solid line, right? So it was look like this, and the composition was plotted on the x-axis and the temperature on the y-axis, right? So this is what we call the phase diagrams. Okay, so in this lecture we will look at more complicated phase diagrams, right? Phase diagrams are very important in determining the solidification process and all the other stuff. Okay, so this is basically, I have explained in the previous lecture also that when we cool uh, the binary alloy, for example, this is a copper nickel alloy, and we start from point A. So, and at point A, you will see that all the particles are all the alloy in liquid, right? Because the temperature is very high. So at that region, you will automatically see that here is only liquid line and the weight percent of nickel is only 35%. But when you move down, when you are cooling, right, when you are cooling at equilibrium, this is basically cooling at equilibrium. This is a controlled cooling. For example, the controlled cooling is, for example, 25 degree per hour cooling rate, right? So this is the ideal cooling rate for the alloys. But more oftenly, we describe uh, this as equilibrium or we control cooling, right? So control cooling is sometimes very better for us because it determines the chemical and physical properties of the alloy, right? So when we move down from point A to B, then we will see that there are microstructure of solids are coming out. And as we move down and we move to point C, then we will see that more of the solid are priming. Similarly, we move to point D, and at point E, it will be all the solid. And one thing you will notice that the composition of nickel in liquid is decreasing while in solid it is increasing, right? At this point. But when you reach here, then the composition of nickel in the solid decreased. This means that more of the nickel is now composed in the solid form, right? And basically, this point from A, B, C, D, this is perfect composition of nickel at 35%, right? 35% weight percent. Okay, so now non-equilibrium are what we call the core structure. For example, if this is my phase diagram, right? And I move down without using the controlled temperature cooling, then we will see that we will have a core structure, right? And in a core structure, we will see that uh, the composition of alpha is not uniform, right? For example, when we take some solid particle from the edges and we examine it, then we will see that there is all the nickel composition is less than 35%, right? But when we look at the center of this alloy, okay, so we will see that the composition of nickel is 46%, right? But when we see at the edges are here or there, then the composition of nickel is uniform, which is 35%. But Why this is happening? What is the reason? The reason for this is when we increase the rate of cooling, for example, when we decrease the rate of cooling, then it means that the particles don't have enough time to diffuse, right? Right? So at the elevated temperature, there is an there is enough chance for the particle to diffuse at one end from the other end. So that's why the coring occurs when we feed at a high temperature cooling rate. Okay, so this is the mechanical properties of the binary system, and especially for the copper nickel alloy which we have formed in the previous. Okay, so the effect of solid solution on string. Okay, on this diagram, we'll see that as we increase the composition of nickel in the alloy, then you will see that it is increasing parabolically, but after 80% composition of nickel, you will see that it is decreasing downward, right? For example, F200 to F2FEF, the value of E tensile strength is 290 megapascal for the pure copper, right? And it is almost almost like 350 E equals 350 megapascal for the pure nickel. Then you will see that at the composition of 60 nickel, right? At composition of 60 nickel and 40 copper, you will see that the tensile strength E is almost equal to 450 megapascal, right? So that's how the strength varies as we increase the composition of nickel. Also, the ductility, or we can quantify it in terms of percentage elongation. When we increase the composition of nickel, then we will see that at 60% it is at its lowest point, because copper is more ductile than nickel, right? So as we increase the nickel composition, then we are increasing the brittleness, right? So as we form the alloy, then its brittleness is increased. Okay, so these are the new type of phase diagrams, right? This is called the eutectic system, and the typical eutectic system will look like this, right? And this point, let me highlight in the red. Okay, so this point is called the eutectic point, and basically these systems are called the binary eutectic system. So the eutectic alloys are what we call the eutectic system. So also the alloys from these diagrams is called the binary eutectic. So in the copper and the silver system, right? So when we dissolve the copper and silver, right, and we plot the composition on the x-axis of silver and on the y-axis the temperature, right? Then we will see some graph like this, right? So basically, this is the liquidus line, right? The liquidus line is not a straight line, but it is a curved line here and then it's curved line here, right? And this will also be an alpha line, right? And this is also a solidus line. And here is liquid and alpha line, right? And this line is, or this region is the alpha plus beta, and this is the beta, right? So on the left, this is alpha, on the right there is beta, above there is liquid, and below this there is alpha plus beta region, right? Okay, so when the copper and silver system they dissolved, then they form the three single phase region, right? So the alpha liquid and beta solids. Okay, so when we see we looked at in alpha the composition, power alpha, the composition of silver is very low, right? And it is mostly composed of the copper. And beta is almost silver. It has less amount of copper, right? Almost no copper in beta. The composition at temperature is Te, right? And there at the eutectic point, there is a reaction occurring that is called eutectic reaction, right? So Ce is basically the composition of the silver at the eutectic point, right? So the eutectic reaction we can write it as like this, as L of Ag, right, is equal to, is in equilibrium, right, with the alpha at Ce plus beta at Ce, right? For example, here is the composition of silver is 71.9 weight% of silver. So we can see that the 71.9% liquid weight percenting of silver, they convert to 8% alpha plus 91.2% of silver, right? Okay, so this is basically another problem, and we are given with that for 40% weight of vanadium and 80% lead alloy at 150 degrees centigrade, determine the phases that present. Okay, so 40%, basically if you see that the x-axis here is SN lead is plotted, right? Okay, so SN, right? So if you moved on at 40%, right, and at 150 degrees centigrade, this is 150 and this is 40, right? So if you look at this point, then you will see that we are at the region of alpha plus beta, right? So our first answer is alpha plus beta. And the second question is, what are the phase composition there, right? So we will draw a tie line, right? And the tie line will extend to alpha. This is alpha line and this is beta line, right? We will extend it to the beta, right? So on the beta, we will see that C beta equal 99 almost, because the composition of Sn is almost pure. It has no lead, right? And on the right, we will see that C of alpha is 11%, right? Okay, so what is the relative composition of each phase? Okay, so we derive a formula there that W of any system equal to for example, if we want to determine the weight percent of alpha, then we will write like this: S divided by R plus S, and similarly beta will be equal to R divided by R plus S, right? So if you perform for the W of alpha, right, then S is basically 99 minus 40, right? So 99 minus 40 is 59, right? So 59 divided by for 40 minus 11, 40 minus 11, sorry, R plus S, so R plus S is 99 minus 11, which is 88, and it is about 67%, right? And W of beta will be 1 minus 0.67, right? So it will be 0.33%, right? So it means that at this point, alpha is 33% and beta is alpha is 67% and beta is 33%, okay? So the lever rule is also applicable here. Okay, so this is a question for us. Uh, we are given with 40% lead and 60% magnesium alloy is heated in the liquid alpha region, right? This is the liquid alpha region. If the mass fraction of each phase is 0.5, then estimate the temperature of the alloy, the composition of two phases, and the composition in the atomic percent weight, right? So for this, you are given with the Pb has a weight mass of 207 and Mg has 24.3 gram, right? Okay, so at 40% weight composition of liquid, we will go off, right, at the liquid plus alpha region, right? Okay, so here we go, right? And we will draw a tie line which will divide the alpha plus beta region into half half because we are given with at each phase 0.5, right? So this is approximately the half, right? And this point, this is the okay, so this is yes, like this. Okay, so if you move down here and we move down here, okay, let me draw the lines again. So this is our tie line, right? Okay, so if we move down and we will notice that here is almost, this is 30 and it is almost 25, right? And if you move down here, then it is 50 and it is almost 54, right? So our first question is, what is the temperature of the alloy, right? So we will draw a horizontal line straight, right? And we will notice that it is just below the half, right? So our temperature is, for the part A, temperature is 200 and, sorry, it is 550 degrees centigrade, right? So part A answer is 550 degrees centigrade, right? And the part B is the composition of the two phases in weight percent, right? So part this, we know it is 25, right? So this is alpha line, so C alpha, and this is the liquid line, so it is Cl, right? So if you want to find the weight percent of alpha, then it will be, let's say this is my R and this is S. So what if you find the weight percent of alpha, then it will be S divided by. Okay, so on this slide I have explained the calculation that how can you calculate the atomic weight percent of the different elements based on the previous information. Okay, so based on the previous information, we found out the concentration of Pb. Okay, so Pb was plotted on the x-axis, so the tie line gave us the concentration of the lead in that alpha, right? So it was 26%. Okay, so if you minus this from 100, so it will give us the concentration of magnesium, right? Because there was only two elements in alpha, right? So alpha was composed of two elements, so it was 26% lead and it is 74% magnesium, right? Similarly, in liquid, we found out that uh, the concentration of lead was 55, right? And if we minus from 100%, right? So it will comes out to be the magnesium concentration will be 45%, right? Okay, and we are also going with the atomic weight percent, right? So it is gram and also it is in grams, right? Okay, so from the previous chapters, you have to remember this formula that if you are given with the atomic weight percent and the composition of each element, then you can find out the percentage of atoms, right? So percentage of atom is C1A2, right? C1A2 plus C2A1. Okay, so you will multiply the opposite sign. For example, if you want to find the concentration of alpha, right? So this is what this is my C1 and this is my C2, right? So C1 times A2. So C1 is 70. So C1 is 74, right? As you can see. Okay, sorry. So this is C1 and this is C2 for this problem specifically because I have done it A1, A2, right? Okay, so C1 is here 74, right? And A2 is 207, right? Plus C1 is 74, 207 plus C2 is here 26 and you multiply with the A1 which is 24.3. So it comes out to be 96%, right? Okay, so this is the atomic weight percent of magnesium in alpha. Similarly, okay, so this region was composed of liquid plus alpha, right? So Fu minus the 100% it will give you the liquid in term of 4% of the lead, right? Similarly, if you want to find the liquid percentage of magnesium, then you will use the same formula, right? But now these, okay, so this is C2, right? And this is C1. Okay, so C1 times A2, so it is 45,207 plus 55 multiplied by 24.3, which is the atomic weight percent of magnesium, right? So it comes out to be 87.9%, right? And Fu minus 1 from this, so it will give you the concentration atomic weight percent of the lead in the alpha solid, right? So it is 12.1%. Okay, so that's for today. See you next time. Thank you. Allah Hafiz.